In this video, we're going to present a formal definition of non-deterministic finite state machines and look at a few more examples. Before we present the formal definition of non-deterministic finite state machines, let's just look at the final, most important result we're going to come to. And that is, for every non-deterministic finite state machine, there is an equivalent deterministic finite state machine. It also goes the other way. These two kinds of finite state machines have the exact same computational power. They describe the same class of languages, which is the class of regular languages. So you don't get any additional power from non-determinism. So for every non-deterministic finite state machine, there's an equivalent deterministic machine, but it might be very large, and it might be kind of hard to find. Let's take a look at an example. We'd like to look at the set of all strings that have a 0 in the second to the last position. With non-determinism, this machine is pretty straightforward to build. Okay. We scan a bunch of 0s and 1s, and somehow magically we know when we are at the second to the last position. Okay, and that's our non-determinism giving us that power to guess right. Then we take this transition, and then we read the last 0 or 1 and end in a final state. There is an equivalent finite state machine and that does the same thing, and here it is. I'm not sure whether you would guess it. I mean, you could try figuring this out on your own. We can kind of see how this thing works. First of all, it's deterministic, because from every state there's a 0 and a 1 labeling edges going out. Okay, so here's the final state, and the key is that in state B can only be reached with a 0. As you can see, we can only get to state B if we see a 0. And then if we see a 1 or a 0, we go to a final state. Okay, if we see more zeros, if we've seen a 0, then we see more zeros, that's fine. The second to the last thing is, our string is ending with a sequence of zeros, so the second to the last thing is a 0. On the other hand, if we see a 1, then we're done, but if we see something more, then we shouldn't accept. So if we see a 0, we go back here, and then we need to see one more thing, and that 0 then will be the second to the last one. On the other hand, if we see a 1, well, we've seen two 1s in a row. To get to C, we see a 1. It's the only way we can get there. And if we see a second 1, well, we've seen two 1s in a row. So we need to start watching for a 0. So you can see this machine will do what we want it to do, but it's not so easy maybe to discover it. Whereas the non-deterministic machine seems much simpler, clearer, and more likely to be correct. Here's another example language that is regular. Every string contains either 0100 as a substring or 0111 as a substring. The problem in building a machine to recognize this language is knowing when to start looking for that, and more importantly, which string are you looking for? And this is a very excellent example for why non-determinism is useful and powerful and gives you some advantage. Okay? Here is a non-deterministic Turing machine to recognize that language. Okay, our initial state, we scan some 0s and 1s until we get to the right place. And then somehow we know whether to take this branch or this branch. These are epsilon edges. And then we can look for the string 0, 1, 0, 0. And if we match it, we then pick up any additional symbols after that. Or we might see 0, 1, 1, 1. Okay, according to the theory, there is a deterministic finite state machine that will recognize the same language. But I'm just going to present it as a goal here, or a challenge to you, to go off and try to build or design a deterministic finite state automaton to recognize this language. We're almost ready to give the formal definition of non-deterministic finite state machines. But before we do that, I want to refresh your memory on some notation and terminology. Remember that the word power set means the set of all subsets. So if we have a set, we can talk about its power set. It's essentially a function that takes a set as an argument and gives you back a set of sets. And it gives you back the set of all subsets. So if our example set is ABC, what are the subsets? Well, empty set A, B, C, AB, AC, BC, and ABC. In general, if you have n elements in a set, then how many subsets are there? For example, if we have 8 elements in a set, then how many subsets are there? Well, you can imagine that each one of these elements is either in the set or it's not in the set. And so you can indicate that by a 0 or a 1. And if you have 8 elements in the set, here we have only 3, but if you have 8 elements in the set, then you have a string of 8 zeros and 1s. So the question is, how many possible strings of zeros and 1s are there with 8 zeros and 1s in them? And if you are a good computer scientist, you know that there are 2 to the 8th, or more precisely 2 to the n possibilities. So there are 2 to the n subsets of a set with n elements. Here we have 3 elements, 2 to the 3 is 8. And why do we need the power set anyway? Well, here's a fragment of a non-deterministic Turing machine. If we're in state Q6 and we get an A, for example, where do we go? Well, we could go to 4, or we could go to 5, we could stay in 6, or go to 8. So that's a set. So if we see an A, we go to state Q4, Q5, Q6, or possibly Q8. So that's the set of places we can go. If we see a B, well, we could go to 4, 7, or 6. 4, 7, or 6. And finally, if we see an epsilon, we have epsilon edges, and we're in state Q6, we could either be in 7 or 8. So 7 or 8. We're now ready for the formal definition of non-deterministic finite state machines. As in the case with determinism, we specify them with a quintuple, a collection of 5 things, but these things are slightly different. We have states, alphabet, transition function, initial state, and final states. But these are slightly different in their definitions, and we'll look at those next. In this slide and throughout these videos, we're going to use this notation. If sigma represents our alphabet of symbols, then we're going to use a subscript of epsilon, sigma sub epsilon, to basically say we're augmenting sigma by adding epsilon to it. So union set of epsilon. So we're adding epsilon. So our 5 elements. We need a set of states, and we need an alphabet. That's the same as before. We need a start state or an initial state. Again, that's the same as before. And by the way I draw epsilons is similar to the way I draw membership, but this is Q0 is a member of the set Q. And we also need a set of accepting states or final states, and this is a subset of our set Q. Now, where we differ here is with the transition function. Given a state that we're in and a symbol of the alphabet from sigma, the transition function tells us which set of states we're going to. So here's the power set. Okay, so we're getting a set of states here. And also, because the epsilon is added to this, if we're in a state and we see an epsilon, this function will tell us which set of states we could go to next. Let's examine this transition function again a little bit more carefully and see how this power set thing works. Remember before when we were talking about deterministic machines, we represented our transition function with a table. Any function whose domain is finite and made of discrete elements can be represented as a table like this. And so with deterministic machines, we could represent our transition function with a two-dimensional table showing which state we're in and which symbol from the alphabet we're looking at. And that tells us exactly one state to go to. So here's an example. Now, with our non-determinism, we've got two changes. First of all, in addition to the symbols from the alphabet, we have epsilon. So if we're in state, for example, Q1, and we see, for example, a B, we go to either Q5 or Q0. And if we see an epsilon, instead, from state Q1, or not if we see an epsilon, but if we choose to take an epsilon transition, we can go immediately to state Q4 or Q3 without scanning any input symbols. If we're in state Q1 and we see a C, the empty set here indicates that we're stuck. We don't have any place to go. So this branch of the non-determinism gets stuck and ends, and we hope some other branch of the non-determinism will accept the string. Now let's talk about how we can execute a non-deterministic finite state machine. How can we check to see whether some string is accepted by the machine? Well, here's a non-deterministic machine, and it accepts all the strings of zeros and ones ending with 0, 0. And if we want to check this string, how do we do it? Well, we could look at it and we could say, well, it does end, and these are the last two zeros, so don't go to B until this point right here. But that's using information that the finite state machine can't use. We can see as humans that we need to take this transition 3 times, 0, 0, 1, and only then do we take this transition. But we don't really have that ability, or I should say the finite state machine doesn't have that ability. So the dumb way to simulate this finite state machine is essentially to put a finger on every state we could be in. So when we see our first 0, we could stay in state 0, or we could move to B. So we have a finger on state A and a finger on state B. Then when we see our second 0, well, we could move to C, or we could move to A, from A to B, or we could stay in A. Okay. So grab another pen here, and so we could be in states A, B, or C. And then when we see a 1, well, there's no place to go from B, there's no place to go from C, and in A, we stay in A. And then when we see another 0, that's this 0, we can either stay in state A, or we can move to state B. And then when we see our last 0, from B we can go to C, from A we can go to B, and from A we can also stay in A. And at this point we've consumed all of the string, and one of our fingers is on state C, so we know that this string is accepted. So here are all the possible states we could be in at any one moment. This is the power set of states. So we're going to show how we can simulate a non-deterministic finite state automaton with a deterministic machine. And what state are we in? Well, it could be any one of these possible combinations. Okay? So if n is the number of states in the non-deterministic finite state machine, what is the number of possible states in the deterministic finite state machine? Well, we have to be able to represent the possibility of being in any possible combination of states. So again, it's 2 to the n. Okay? It's a large number in general. The equivalent deterministic finite state automaton for a non-deterministic finite state automaton could have as many as 2 to the n states. In general, it won't be quite, in most cases it won't be quite that bad, but in general it could be pretty bad.